In this video, we're going to take a look at multiple linear regression. This video follows a few other videos where I was looking at optimizing feature selection, so I'm going to work with a few notebooks that I've already been working with. First of all, what is multiple linear regression? Well, we're trying to predict an outcome variable, which we'll call target, or oftentimes y, based on a set of predictors, which oftentimes we'll call x. And this will give us a formula, kind of like we saw back in algebra, where y equals some coefficient plus some coefficient times the first feature plus some coefficient times the second feature, on and on and on and on and on, all the way up to error. So in regression, we're trying to estimate what those coefficients are and trying to choose which predictors to include, where we can use topics I covered in those previous videos like the random forest and the RFECV. Several other features, also exhaustive search, forward selection, backwards elimination, several options we can look at there. And we'll use quite a bit of the scikit-learn library in Python to make this work. So exploratory modeling is kind of neat, and I think it's not often considered, or it's not the first thing that comes to mind when we're thinking about regression. But really, exploratory modeling is looking at these coefficients and saying, okay, these are certain inputs that will give us an output that we desire, but what is the most effective input? And I think we see this a lot in decision making and also in governance, where you might have somebody running for office who says, I want to spend a lot of money on education because that creates jobs, and somebody else says, I want to spend a lot of money on maybe turning a farm into an industrial park because that will create jobs. They both might well create jobs, but the question is, which one is the more effective for the money that you're spending? And that's where exploratory modeling comes in. Now, predictive modeling is what we tend to think of a bit more when we think about regression, which is, okay, given the x or given the features that we have, what do we predict that y will be? So what we'll typically do is use a training set to create the model and a testing data set to test out our validations and get an accuracy score. All of this I'll show when we do go hands-on in just a moment. After that, we can feed new records into that model because the model has been trained. And when we're looking at the accuracy of the model, we're often looking at the ordinary least squares method. So distance between prediction and actual results. It's fairly straightforward to get the coefficients if we want to do exploratory modeling, as we saw just a moment ago. After we do a regression analysis, we can just ask it for the coefficients, and that's effectively what makes up that line equation that we saw a few slides ago. So with all that being said, let's jump right in. I'll start with a linear regression example. So in a previous video, I imported this blueberry data frame, and it's a look at certain inputs and how they impact blueberry yield. I removed a few columns I didn't want, and I made that a smaller data frame. Next, I scaled the data using a standard scaler. So what that does is it takes every data element and subtracts from it the mean of that column, which basically sets the mean to 0, and then divides by the standard deviation. So we're looking effectively at a similar scale across all of our features, no matter what the scale happens to be. When I do this, I'm dropping out the yield column because that's the target that we're trying to predict. And these are the features that we're using to predict this target. If you notice here, there are, looks like about 13 elements in each of these square brackets, and that matches up with the 13 predictors that we have here. So this is a look at the data frame after it's scaled without any kind of columns or label titles on it, but it's still the same data, simply scaled. Next, we do the train test split, which is where we take our data and now we divide it into a training data set, which would be 70%, and a testing data set, which will be 30%. After that, in a previous video, I did our recursive feature elimination with cross-validation and also random forest to find out what the best features are, and it gave me a list of 13 features. Now, I borrowed this regression summary from a different notebook that I have. This will give us a few statistics after we run the regression. And finally, guess what? It's time to run the regression. Because this is a continuous variable, which is yield, so it's a number that could be fractional in any kind of range instead of kind of like a categorical number or grouping of numbers, I'm using linear regression. So I take the linear regression, and fit is what trains the model. I pass in the X training that we got from our train test split, and the Y training. So effectively, the columns with the features and the single column we're trying to predict. And after that, I print out the coefficients, which is what makes up that formula that we saw on the presentation just a moment ago. So what do we multiply by each of the features? And then do a little prediction and print out a regression summary. So we'll go ahead and let that run again, and you see below, coefficients here are fairly large, and it's interesting, several negative and positive coefficients, but nonetheless we have what we can use to put together a formula. What might be interesting is to tweak this a little bit by trying different combinations of features and seeing what we get out of it. And after that we get our regression statistics, the mean error, root mean squared error, so on and so forth. Now let's take a look at logistic regression. So logistic regression is ideal for a categorical variable. And here in this data set, I've made a categorical variable, which is counties in the United States that have historically voted for third-party candidates more than the average county vote within the United States. So the idea here, kind of thinking current events, is that I'm a third-party candidate and I need to get on the ballot in 50 states. And so I want to find out certain information about where I should send petitioners to get ballots signed, to get petitions signed to get me on the ballot. And also within those counties, where should I go? Should I skew towards maybe a concert or a concert that impacts a certain demographic? So this is the kind of decision making we could get out of this. And in this case, what I did is I made a third-party percent column just by looking at the vote in 2016 when there was a stronger than usual support for third-party candidates, and came up with that percent. And then I made another column, third-party county, which is simply a 0 or 1, like a Boolean column. And if it's a 0, that means that county voted less than average for third-party candidates. If it's a 1, it means that county voted more than often for third-party candidates. And that gives us our categorical value. Because it's either a 0 or a 1, it's not a range between the two. We find the average in the U.S. at that time, county by county, was 5.22%. Next, I make a bit of a smaller data set with some demographic data that I'm going to use. I put this through both random forest and RFECV. And there were certain columns I eliminated because there was cross-correlation, and certain columns I eliminated just to get to a core model. And what I ended up with is total population, age 29 and under, age 65 and older, median household income, unemployment percent, less than high school percent, less than college percent, and rural percent. That plus the third-party county. After that, do a bit of scaling, just as we did before, so that everything is on a 0 mean, and we're looking at a similar set of units from one feature column to another. Next, we split into our training and testing. So we start with the scaled data. We tell it what the column is that we're trying to predict, which is it a county that has voted more often than not for third parties, or more than average for third parties or not. And once again, the test size of 30% rather. So after that, we come down here, and the logistic regression is quite simple. We just instantiate the logistic regression class, save it into this variable called model, and then train it with model.fit. And after we've trained it, we can pass in the testing data and see what it predicted. And because this is testing data that came from the same source as our training data, we know what the actual results are. So after that, we can go through and do accuracy, precision, recall, and F1. And we see, okay, all of these hovering around 75%. And now we have our confusion matrix where we have true positives, false negatives, and true positives. We want these numbers to be much bigger than these numbers, and indeed they are. 75% accuracy, that's good, no doubt. It would be nice to have something a little bit stronger, but I did throw out several feature columns here, so there's several different ways I could play around with this. Also, what might be interesting is to change my classifier column. I said greater than the mean of third-party vote across counties in the U.S. Might be interesting to step that up a little bit and say it's at the 75th percentile and greater. So we're looking not just at those cases where a county was maybe a little bit more than average on third-party, but those that tend to really skew towards third-party. But then again, if we're doing some exploratory analysis where we want to take a look at the coefficients, accuracy isn't necessarily the biggest thing that we're looking at. But nonetheless, that's a look at regression, both linear and logistic. I think this stuff is really cool. I really enjoy taking a look at the relationship across data and how it can be used to make predictions. So I hope you find it fun as well. Thank you.